Good morning, everybody, and thank you to the organizer of the conference to give the opportunity to fermentees to present this work about a neutral alcohol base for seltzer production. This presentation will be divided in 4 parts. In the first one, I'm going to present what is a hard seltzer. In the second one, I'm going to discuss about what is behind the hard seltzer phenomenon. In the third one, I will present how to produce a neutral alcohol base. And finally, in the last one, I'm going to present the result we have obtained during the study of the characterization of spring-ferm NAB2. So what is a hard seltzer? Hard seltzers are alcoholic beverage with approximately 5 to 15% of ethanol, containing carbonated water, alcohol, and often fruit aromas. Alcohol can come from fermentation or pure food grade distilled alcohol. So, to obtain a hard seltzer, you can have a base with a low gravity neutral alcohol base that is without flavor, without color, and a carbonation and flavors. Or you can have a base like a medium to high gravity neutral alcohol base without flavor, without color, and that will be diluted with deaerated and carbonated water and added with flavors. So in fact, a neutral alcohol base is free of flavors, free of superior alcohols, free of esters and other volatile compounds, and without colors. And in fact, NAB is close to water but with alcohol. So what is behind the hard seltzer phenomenon? So hard seltzer are around more or less 5% of ethanol, containing 100 calories per can, 1 to 2 grams of sugar per can, and these products are vegan and gluten-free. In the United States, in 2019, hard seltzer account around 2.6% in volume of total alcoholic beverages, and in 2018 it was only 1%. So how to produce a neutral alcohol base? You can use a medium with malt or molasses. So this kind of medium is rich in nutrients, minerals. He has got buffer power, but the product you can obtain with this kind of medium will contain a lot of flavors and will be colored. If you used a pure sugar medium, this medium will not contain nutrients, no minerals, and it has got no buffer power. But the product you can obtain will be low in flavors and without color. So how to ferment pure sugar solution? First, with a selected yeast strain with a high robustness, low aroma production, and fast. But we need also a design culture medium with a nitrogen source, a buffer power, and a lot of nutrients, vitamins, and minerals. Spring-ferm NAB can bring all these elements. So now I'm going to present the study and the results about the characterization of spring-ferm NAB2. So to evaluate and study all these, the impact of all these parameters, we built a design of experiment with 30 conditions repeated with 3 different products: SAF Spirit AG1, SAFENO VR44, and SAFENO HDS62. For the different factors, we studied different levels. For the concentration of NAB2, for example, we studied 3 levels: 200 grams per hectoliter, 375 grams per hectoliter, and 550 grams per hectoliter. For the pitching grain, we also studied 3 levels: For the sucrose, we studied 5 levels, and for the temperature, 6 levels, from 20 degrees to 35 degrees. The fermentation have been performed on an on-com system, which allowed to follow online the measurement of CO2 production. And different responses have been analyzed, like ethanol production, residual sugars, fermentation duration, productivity, ethanol yield, the concentration of glycerol, the concentration of different organic acids, the biomass production, the higher alcohols production and ester production, and also the SO2 production. And the analysis of all these data allowed us to build a model with the analysis and the statistical analysis of all these data. And with this model, we can predict some conditions of fermentation, optimize some condition of fermentation. So if we concentrate on the ethanol response, for example, we can see on this graph that, for example, for the first one, we have a strong and robust model because the R2 is close to 1. And on the second graph, we can see that we have a good predictive quality with a Q2 close to 1 also. We can see also on the second graph that the sucrose added has an impact positive on the production of ethanol, as well as the NAB. But we can see also that the temperature has an impact, positive impact on the production of ethanol, but we have to work at the low temperature. Concerning the response on ethanol production, we have also this graph. And there we can see that on the first graph that when we increase the sugar concentration, we increase also the ethanol production. On the second graph, we can see that when we increase the concentration of NAB, we also increase the ethanol production. And we can show on the third graph that the temperature impacts the ethanol production, above all at high temperature. On the graph on the top, on the right, we can see that the temperature inhibition is enhanced at high concentration of sucrose. It is the curve in blue. And in the graph at the bottom, which is a comparison of the different products, we can see that Fonchy-Penot VR44 and the Fonchy-Penot HDS62 performances are better at low temperature, while the temperature inhibition is lower for SAF spirits AG1 strain. So now another representation of the results with the ethanol production with the strain HDS62. So in the different graph, we have the production of ethanol with the combination of the different parameters. So on the graph in red, we have got the high production of ethanol, and in blue, the low production of ethanol. On the vertical axis, we have got the temperature of fermentation, and on the horizontal axis, we have got the sucrose concentration in the medium. The graph at the bottom is for the pitching rate, the low pitching rate, that is to say 500 milligrams per liter. And at the top, it's the graph with the high pitching rate, that is to say 2,500 milligrams per liter. And all these graphs concern the production with NAB at a concentration of 200 grams per hectoliter. And as we can see on this free graph, the high production of ethanol is obtained at the high concentration of sucrose and at the low temperature. But now, if we concentrate on the over quantity of NAB we can add in the culture media. We can see that the area in red and orange increase because we can produce more ethanol, but it's always in the same area of the graph, that is to say for the high quantity of sucrose and the low temperature. And if we increase the quantity of NAB too, we can see that the area is increased also, and we can obtain 18% of ethanol in different cases. We can see also that if we increase the pitch rate, we are not going to increase the production of ethanol. So after this, the collect of all the data, we have built a model, but we have also to validate this model. So to validate this model, we select different points at different parts of the model, an optimum about the productivity, another optimum for the production of ethanol, and another optimum that is going to link productivity and the titer of ethanol. In the graph, you can see that you have got in blue the experimental point, and in the green, you have the predictive point. And as you can see on the graph, the blue point and the green point are very close, so we can say that the model on ethanol production response is validated. Now, if we study another parameter like residual sugar, we can see that the model is quite robust. The R2 is also close to 1, and we have also a good predictive quality of this model. And for this parameter, we can see that when we increase the concentration of sucrose in the medium, the residual sugar are very important. But if we want to decrease the residual sugar, we can see on this graph, we have to increase the quantity of NAB. So now different graphs that are going to summarize the previous results. On the first graph, we can see that when we increase the quantity of sucrose, we also increase the quantity of residual sugar. If we increase the concentration of NAB, we tend to reduce the residual sugar. If the temperature increases, we also tend to increase the residual sugar in the medium. And on the graph on the right, we can see that the AG1 strain is the most performant strain at high temperatures, because the residual sugar for the high temperature are low comparing to the concentration of residual sugar we can obtain with the VR44 and the HDS62. Now the surface response for this parameter. Like previously, we have got different graph with different color. On this graph in blue, we have got the area where the residual sugar are very low, and in red, where the residual sugar are quite important. So in the vertical axis, we have got the temperature of the fermentation. On the horizontal axis, we have got also the sucrose concentration. The first three graphs concern the NAB at the concentration of 200 grams per hectoliter. The graph at the bottom is for the low pitching rate, that is to say 500 milligrams per liter. And at the top, we have got the graph for the high pitching rate. And now you have also the evolution of the different area when we increase the quantity of NAB in the medium. And as you can see, we have got the high concentration of residual sugar always in the same part of the graph. That is to say, when the quantity of sucrose added in the medium is very important, and for the high temperature. So if we want to reduce the quantity of residual sugar in the medium, it's better to work at low temperature. So, like for the ethanol production, we have also to validate the model based on the residual sugar. So we also selected different optimum at different parts of the model. One for the productivity, one for the titer, and another one with the productivity linked to the production of ethanol. On the graph on the right, we can see the experiment point comparatively to the predictive point. So the experimental point is in blue and the predictive point is in green. And we can see that the blue points and the green points are very close. So we can see and say that the model based on the residual sugar response is validated. So all this data allowed us to build different models, and with these models we can do different things, and for example we can optimize some process. So here an example with the strain VR44. So if we want to reach a titer of ethanol upper to 17.5%, we have to work in the green area, that is to say at low temperature and with a high concentration of sucrose. Now, if we want to have less than 5 grams per liter of residual sugar, we have to work in the green area, and we can reach this concentration of residual sugar with the VR44. Now, if we want at the same time the two results, we have to work in the common area, which is in green on this graph, that is to say at low temperature and with a high concentration of sucrose. We can also add another parameters, for example, the duration of the fermentation. And if we want the duration is above 160 hours, we have to work in the green area. And now, if we combine all the parameters, the common area is in green, and now we know that we have to work with these parameters to reach these answers. So all these models are very interesting, very useful to improve your process for the production of neutral alcohol base, and the fermentist team is here to support your trials, to give you some advice, so do not hesitate to contact it. Thank you for your attention.